Okay, in this video I'm going to introduce you to the extended part of the symbolic language. So we've got my slideshow here that we'll get going, and we're going to enrich the language and an introduction to predicate logic. This is the material that is introduced in chapter 5. So that's the chapter you should be reading, and in another video I will go over chapter 5 in some slides to talk about what you need to pay attention to there. So recall that in statement logic, in the language SL, we use capital letters to represent simple statements. That's what you've been doing for most of the semester so far. Remember that a simple statement contains no logical expressions. More specifically, a simple statement does not contain words not, if then, if and only if, or anything being used equivalent to one of those. And as you know, for example, in the case of a statement like Sam is happy, you would symbolize it just using a single statement letter. For example, the letter S could be used. Now we're going to develop the language more and give it more expressive power. We're going to dig deeper into the English language, because that's the language we're using most of the time as our natural language. So in predicate logic, we'll call this PL. We increase the expressive power of the formal language by including new symbols that capture the concepts of all and there exists at least one. These are called quantifiers. We're going to capture the concept of non-gendered pronouns. These are called individual variables, represented by the lowercase letters U, V, W, X, Y, and Z. What a pronoun is, it's like the word it. It stands in place of a noun, and we'll see soon why that's important for us. We're going to capture the concept of names of individual objects. These are called names or individual concepts, represented by lowercase letters A through T. And finally, we're going to capture the concept of properties of objects and relationships among objects. The symbols that do this are called predicate symbols, represented by capital letters. So capital letters are not going to be used so much anymore to represent whole statements. We're going to change the way we use capital letters. So transitioning to predicate logic. So instead of starting by throwing out the whole language, let's begin with some examples. Let's use again the example Sam is happy as a starting point. In predicate logic, we do a few different things. We use a symbol to represent the property of being happy, and we use a symbol to represent Sam. So the first one is a predicate symbol, the second one is an individual symbol, individual constant. So we said that we're going to use capital letters to represent properties, lowercase letters to represent individuals, and so let's apply that idea here. So for the property of being happy, let's use the symbol capital H. And we can use the lowercase letter S to represent Sam. S is being used as another name for Sam. So we want a symbolic expression that shows that the property expressed by S applies to the individual object named by S. Expressed by H applies to the individual object denoted by S. We want something that says, in effect, H applies to S, or S has the property H. And so the syntax, the grammar for predicate logic is going to look like this. It's not going to bounce, but the capital H is put next to the lowercase s, and it means that the property expressed by H applies to the object denoted by or referred to by S. It says, in effect, Sam is happy, or that the property H applies to the object denoted by S. So in SL, we give an interpretation. An informal interpretation is where we say, for example, S stands for Sam is happy. And we have to do something similar here. To say H stands for the property of being happy, our little informal interpretation will be this. HX means X is happy. And I'll explain in a second what the X is doing there. To indicate that S stands for Sam, we'll write little s, colon, Sam. The lowercase letter s stands for Sam. Now, the expression HX contains that lowercase x, which is a variable. In this case, x is just a placeholder. It's just indicating that something needs to go next to h, that h is what we call a one-place predicate. To say it's a one-place predicate just means that there's a space on the right where an individual symbol goes. H standing by itself would be a statement later. HX indicates that the expression H is going to be used as a predicate symbol to stand for a property that applies to something that goes next to it. So when we give the informal interpretation, we write HX, indicating that H is a one-place predicate, namely happiness. This is an informal interpretation because a formal interpretation is much more complicated. As you recall, in statement logic, an interpretation is really an assignment of truth values. An interpretation in predicate logic is rather more significant, and we'll get to that. I beg your pardon. So let's make a bigger interpretation. We'll keep using H to stand for is happy, but we'll introduce some more people. Sam, B will stand for Betty, A will stand for Arthur, and we can use this plus the truth functional connectives to make longer statements. For example, HS and HB and not HA. So it's very similar in a sense to statement logic. If you had statement logic, this would be three different statement letters. But here we have one predicate symbol and three different names, three different individual symbols. It says Sam and Betty are happy, but Arthur is not happy. If this were statement logic, it would have to be like capital S, capital B, and negation of capital A. You would use those three letters. But here you get H applies to S, H applies to B, but H does not apply to A. This is going to be very, very useful to us later on down the line when we explore more properties of statements and relationships among them. In addition to one place, also called monadic predicates, we have n-place, or n-adic, or polyadic expressions. In other words, that means we can have more than one place predicate symbols. So for example, take the statement, Harry loves Sally. There are two people in the relationship of love. Harry loves Sally. So that's the relationship between Harry and Sally. So we can use, in statement logic, the note here says you would use a single statement letter. In predicate logic, we have to introduce a two-place predicate symbol. So let's use LXY. LXY means when you write an individual name in place of the X and put a name in place of Y, it means the thing named by the left-hand side loves the person named by the right-hand side. So if we use H to represent Harry and S to represent Sally, then Harry loves Sally can be written as LHS. The relationship L applies to H and S in that order. LHS says Harry loves Sally. And we can introduce connectives. For example, LHS and not LSH, which means, sadly, that Harry loves Sally, but Sally doesn't love Harry. Okay? So the idea is pretty straightforward, I hope. Things get a little bit more complicated when we add quantifiers and variables, and you'll see how this goes in just a minute. So PL allows us to dig more deeply into the subject-predicate form of a simple statement than is possible with SL. So here's what I was getting at earlier when I talked about interpretations. In SL, we provide an informal interpretation of a set of statement letters when we indicate what statements the capital letters represent. More formally, an interpretation in SL is an assignment of truth values to statement letters. Remember that when we talk about truth tables, for example, the capital letter A, we say it has two interpretations. It could be true and it could be false. When we take two statement letters together, we say that there are four possible interpretations, A and B both true, A and B both false, or having opposite truth values in different order. Similarly, when we give a list of PL expressions and indicate the properties and individuals that each one stands for, that's informal. A formal interpretation is more involved. And I'll return to that later in the course. We're not going to do it today, and you need to sort of understand how the language works before you get into the more formal details of interpretations. So let's talk about quantifiers. That's the final piece in predicate logic. Intuitively, a quantifier is an expression that tells us how many of something. It's not really the best or most accurate way of looking at a quantifier, because in logic, the things we call quantifiers just really tell us the following. They tell us all or some, but the word some has a special meaning in logic. Some doesn't really mean not all. Some doesn't mean only some. Some means there exists at least one. So let's look at some examples here to get an idea of what's going on. Let's start with all. This is the universal quantifier. In logic, when we talk about all of something, we're using universal quantification. So take us the statement, all fish are swimmers. And if you remember from the beginning of the course, we took statements like that. We had all ancient astronomers are stargazers, or all humans are mortal. All fish are swimmers can be represented like this. All F are S, where F is the set of fish and S is the set of swimmers. The statement asserts that all of the fish are swimmers, and that's the universal quantification. Now, we want to represent this in PL. So we need a formal symbol that represents the universal quantification, but we have to build up to that. So first of all, let's take all F are S. To represent this, let's revise the grammar to express the idea that if something is an F, then it is an S. So that is to say, the statement, all F are S, all fish are swimmers, you can say that in a different way. You can say, if something is a fish, then it is a swimmer. The sentence, if something is a fish, then it is a swimmer, means the same thing, that all fish are swimmers. So here, something and it are pronouns. They take the place of nouns, names of objects. When you say, if something is a fish, then it is a swimmer, both something and it in that sentence, those are pronouns. And those are what are going to be replaced by variables. So we can put it like this. Even more formally, we can say, if something, X, is an F, then that thing, X, is also an S. That is, for any X, if F applies to X, then S applies to X. All F's are S's is take anything you want, call it X. Whatever X you pick, if F applies to that, then S applies to that. If the X you pick is a fish, then the X is also a swimmer. Or using PL symbols, let's plug in the predicate symbols. For any X, if Fx, then Sx. See, we've replaced F applies to X by Fx. We've replaced S applies to X by Sx. So here we are with what we just had at the bottom of the previous slide. And now we need a symbol. Well, we have to add some propositional logic symbols too, some SL symbols. Let's add the symbol for the conditional, right? We could make it more Loglish-like by writing for any X, if Fx, then Sx. We put in the arrow for the conditional. And now we need a symbol for the for any X, for the universal quantification. And the symbol we use is the upside down A followed by a variable, in this case X. We write upside down AX, Fx arrow Sx. And the way you read that is just like you read the string at the top of the page for any x. If fx, then sx. In other words, it just says all f's are s's. The upside down a is called a universal quantifier, upside down a for all. When used, there must always be a variable to its right, as in for all x, upside down a x. In this expression, the x is called the quantified variable, or the variable of quantification. The other quantifier, so first we have the universal quantifier. Now we're going to have the next quantifier, which is called the particular or existential quantifier. Instead of talking about all SRP, we're going to look at how we say there's at least one S that is a P. And I have some brief discussion here why it's called a quantifier. It's because sometimes to say there is at least one, we sometimes just say some. Some can mean only some, or it might mean some, to say some S or P, with a background understanding that some S or not P. Sometimes we talk that way. In logic, the word some is always interpreted just as there exists at least one. It doesn't necessarily mean there are some that are not. It only means at least that there are some that are. At least one that is. So let's cash that out a little more. Let's look at a statement like, some children are hockey players. Using C to represent children and S to represent hockey players, some C are H. Now, we're going to incorporate our PL symbols, right? We're going to interpret it as there exists at least one C that is an H. So we get, there exists at least one thing X, such that CX and HX. That just means there's at least one thing that has both the properties C and H, the property of being a child and a hockey player. And again, using SL connectives, there is at least one X such that CX and HX. Move that to the top. And now we need to complete this by introducing a symbol that stands for that string, there is at least one X such that. That string, there is at least one X such that, is an existential quantification. We need a symbol that represents that, and that will be the backwards E for exists. There exists an X such that CX and HX. At least one X that has both the properties C and H. The placement of the parentheses is really important here, and I'll come to that, not in this lecture, but in another one. Basically, it's similar to the negation. If you took off the parentheses, the existential quantifier would just attach itself to the CX, and the HX would be have a blank X there next to it, and I'll explain that more later. So with any universally quantified statement of the form all A or B, we can represent any statement of the form some A or B by using a pattern like the one given here. Now let's collect some more information. There are actually four classic types of quantified statement. Historically, logicians wrote that there are four basic categorical forms of quantified statements, usually labeled A, E, I, and O. A is the universal affirmative, E, the universal negative, I, the particular affirmative, and O, the particular negative. Universal affirmative, all A's are B's. Universal negative, no A's or B's. Particular affirmative, some A's are B's. Particular negative, some A's are not B's. For a long time in logic, some logicians thought this was the only possible way to do quantification. Things are known to be much more rich and complicated than they were once thought to be. So although this is no oversimplified view, the four forms do regularly recur. Any statement taking one of these forms can always be symbolized in a similar way. So let's go through these. So each one of these has a standard representative. The universal affirmative, all A or B, can always be symbolized like that form on the right. Here, curly A and curly B with the X next to them just means you got some expression containing an X, that is the A part, and you got some expression containing an X, and that's the B part, when you put it in predicate logic. So all A's or B's would be for all x if AX then BX. Universal negative, no A's or B's, would be expressed as for all x if x is an A, then x is not a B. Some A's or B's, as we saw similarly earlier, there exists an x such that it is an x and it is a B. The particular negative, some A or not B, means that there exists at least one x that is an A but it's not a B. AX and not BX. Now let's take some examples of each of these. Start with the universal affirmative. All A or B can be expressed as for all x if AX then BX. We can take all humans are mortal. And here you have for all x if HX then MX, where is a human is HX and is mortal is MX. Now let's make a more complicated left-hand term. All green rocks are pretty. So now the left-hand predicate expression is green rocks. So to be a green rock is to be green and to be a rock. So that's going to be a more complicated expression. For all x, if x is a green rock, that is, if it's green and a rock, then it is pretty. And finally, we can make the right-hand side more complicated also. All square tables are inexpensive and useful. So we have for all x, if Sx and Tx, if something is it is square and it is a table, then it is inexpensive and it is useful. Got a dry cough here. So let's go back. All A or B, A goes where the humans are, and in the symbolic expression, that's the AX and HX. And on the other side, when you have the B and the mortal, the B corresponds to the mortal. In the symbolic expression, the B goes where BX does, and the mortal goes where the MX is. And we can do that with each of these. As you can see, for the more complicated expression, A, green rocks, goes where the AX goes where the GX and RX is. And similarly, the right-hand side corresponds. And finally, in the final expression, square tables goes where the A is, that's where the AX is, that's where SX and TX is. That expresses being a square table. And the right-hand side, inexpensive and useful, is put together in conjunction there in that final statement. So we get a similar form for each of these. AX goes on the left, the BX goes on the right, and they all represent the all A or B form. All of these are some version of all A's or B's. They all have the same basic shape. Let's look at the universal negative, and we'll go a little more quickly now. No A's or B's, no humans are mortal. We do the same thing we did before. HX for is human, MX for is mortal, but this time there's a negative in front of the B part. And that applies to no green rocks are pretty, looks the same. No square tables are inexpensive and useful. For all x, if x is a square table and it's not both inexpensive and useful. There's an ambiguity in there that I'll get to when I get to the O-type statement. I'll talk about it a little bit. Particular affirmative, and we'll deal with the ambiguity in connection with the particular negative. Particular affirmative is some A are B. Some examples are some humans are mortal. There is an X, HX, and MX. Some green rocks are pretty. Again, we're using GX and RX to mean green rock, PX to mean pretty, and we get an instance of that form above. And finally, the same thing happens with some square tables are inexpensive and useful. Finally, the particular negative. And here's where there's an ambiguity with the negation there. So let's look at our examples. Some humans are not mortal. There is an X such that HX and not MX. Some green rocks are not pretty. There is a GX and RX that is not an MX and not MX. Some square tables are not inexpensive and useful. There exists an X such that SX and TX, and it's not the case that, and notice how I've interpreted that as both inexpensive and useful. And that really is perhaps the only way to do it if it's going to be in the O form. So let's focus on that a little bit. Some square tables are not inexpensive and useful. Let's just put that part that contains the ambiguity at the top, and notice that it's ambiguous. It could mean that something is not expensive but it is useful. Not expensive and useful. Some square tables are not inexpensive and useful might mean they're not inexpensive, but they could be useful. They're not both inexpensive and useful, and that's how I interpreted it in the example. It could mean they're not inexpensive and not useful, which we would express as a negation of a disjunction. The first one would be not I and you. The second, not both I and you, Ix and Ux, and not either Ix and Ux, which means neither nor. So the one that really can't be right is the one I've highlighted here in green. So let's see why that is. If this is meant, then the form of the original statement isn't really some x are not b. It would really be in the form some a are b, because it's being a non-I and a u, right? That's what the b would be. So the only way the statement has the O form, the original statement, is when the whole statement or formula following the ampersand is negated. So when you think about how to properly symbolize a statement, you can use your knowledge to detect ambiguities, and you can, by doing that, you can either request more information from the author if it's not clear, or provide, if you are the author, greater clarification to ensure that the correct meaning is conveyed. Okay, that's the briefest of introductions to what we're doing here. That's enough for right now. The way you're going to really understand this is by working through examples, and I will be posting some homework problems.